The nearest star to Earth, Alpha Centauri, sits just 4 light-years away. To reach it at the speed of a bullet, 1 kilometer per second, the journey takes about 120,000 years. Want to get there in a human lifetime, say 40 years, the spacecraft must travel at 10% the speed of light, 30,000 kilometers per second, fast enough that a speck of dust hits like a grenade. Now here's the brutal calculation that may entrap every civilization in the cosmos forever alone. To reach that velocity and slow down at the other end using the most efficient chemical reaction physics allows, the required fuel tank would weigh more than the observable universe. Not more than Earth, not more than the Sun, more than all the stars, galaxies, and black holes that exist. That's not an engineering challenge, it's a law of nature. And it might mean intelligent life everywhere is imprisoned, each species alone, forever, on its own cosmic island. This comes from a single equation governing every journey through empty space. To move in a vacuum, something must be thrown backwards. Conservation of momentum pushes the spacecraft forward. But here's where the nightmare begins. To throw that mass, it must first be carried. Carrying mass requires fuel. That fuel needs fuel to carry it. The mathematics is exponential. Every factor of 2.7 increase in velocity requires roughly a 10-fold increase in starting fuel mass. Double that speed increase, 100 times the fuel. Triple it, 1,000 times. The numbers escape sanity within a few doublings. This single relationship, called the Tsiolkovsky rocket equation, explains why you stand on Earth looking at stars you will never visit. In 1903, while Einstein was developing relativity and the Wright brothers were testing flight, a self-taught Russian schoolteacher named Konstantin Tsiolkovsky sat in his log cabin working through calculations by candlelight. He wasn't building rockets, he was dreaming, asking whether humanity could ever leave Earth. What he derived was simple but devastating. Final velocity depends on 2 factors: exhaust velocity, how fast propellant shoots out the back, and mass ratio, how much heavier the rocket is at launch than at arrival. That mass ratio sits inside a logarithm. Logarithms are the inverse of exponentials. To get steady increases in speed, you need exponential increases in fuel. Tsiolkovsky calculated that reaching orbit would require a rocket about 90% fuel by mass. His contemporaries found this absurd. Rockets made almost entirely of fuel? 6 decades later, the Saturn V carried humans to the moon. It was 85% fuel. Tsiolkovsky had looked into the future and seen exactly what physics demanded. But reaching orbit is the easy problem. Orbital velocity is about 8 kilometers per second. Getting to Alpha Centauri in 40 years requires 30,000 kilometers per second, nearly 4,000 times more. And exponential growth is merciless. Run the numbers. Reaching 10% light speed with hydrogen-oxygen rockets would require starting with approximately 10 to the 40th power kilograms of fuel. That number has more zeros than there are atoms in the sun. This is why science fiction invented warp drives. Within real physics, there's no escape. So what about nuclear? In the 1950s, a team at General Atomics, including physicist Freeman Dyson, designed Project Orion, a spacecraft pushed by nuclear explosions. Detonate a bomb behind a massive steel plate, ride the shockwave, repeat every few seconds for years. It sounds insane. The physics was impeccable. Nuclear blasts provide exhaust velocities roughly 10 times higher than chemical rockets. The equation becomes less cruel. Dyson calculated that an Orion ship massing several million tons could theoretically reach Alpha Centauri in about 130 years. It would consume a nuclear bomb every 3 seconds during acceleration. The total arsenal required would dwarf every weapon humanity has ever built, and 130 years still exceeds a human lifespan. Nuclear power transforms impossible into merely implausible. Modern spacecraft use ion drives, charged particles accelerated to extraordinary velocities. The efficiency seems remarkable, but physics demands a trade-off. High exhaust velocity produces microscopic thrust. An ion drive at full power pushes with less force than a falling paperclip. It would take a week to accelerate a coffee cup to walking speed. Ion drives cannot deliver humans to the stars. What about skipping fuel entirely? The breakthrough Starshot project proposes sailing to Alpha Centauri on a beam of light. A giant Earth-based laser pushes a gram-scale probe with a gossamer sail, no fuel aboard. The physics works, barely. A 100-gigawatt laser firing for 10 minutes could accelerate a 1-gram probe to 20% light speed. It would reach Alpha Centauri in 20 years. But the probe cannot slow down. It screams through the system in hours, gathering what data it can before vanishing forever. And nothing larger than a postage stamp could ride that beam. The rocket equation has variations. None of them set you free. So here's the question haunting astronomers. Where is everybody? If intelligent life exists elsewhere, and the chemistry suggests it should be common, those beings face this identical equation. Momentum conservation isn't a human invention. It's woven into space-time itself. Physics operates the same way around every star in the galaxy. Every civilization that looks at its night sky and dreams of visiting those lights confronts the same exponential wall. Every species smart enough to derive the equation is smart enough to understand what it means. The Milky Way might be teeming with intelligence, billions of civilizations, each trapped in their home system, signaling into the void, receiving signals centuries after the questions were asked, knowing others exist, but understanding, truly understanding, that meeting is impossible. The rocket equation answers Fermi's paradox. The cosmos is lonely because the cosmos is vast, and physics offers no shortcuts. And yet, light itself travels without fuel. Photons cross billions of light years, bringing information from the edge of existence to your retina. The James Webb Telescope captures light that was already ancient when Earth formed, arriving effortlessly at senses no larger than a tennis court. The universe can be seen, it can be understood. The same laws that imprison matter let information flow freely. Perhaps that's the fate of intelligences everywhere, to be witnesses rather than travelers, to comprehend the cosmos without inhabiting it. The rocket equation isn't a problem waiting for a clever solution, it's a truth about the universe as fixed as the speed of light. Understanding it changes the experience of looking up. That starlight reaching your eyes right now completed a journey your body never will. It went where nothing carrying you could follow. Knowing that, the light feels different. It carries something fuel cannot provide, connection across distances that matter will never cross. Like if this was interesting, hit the subscribe for more and turn that notification bell on.